Okay, so in this video, I want to discuss the Weierstrass function, which is just one of my favorite topics in math because it's just a question which you can very naturally ask. And if you sort of follow your nose, then you're led to this function which has some nice properties. And you get some really interesting geometric consequences for free, which you never even expected to begin with. So what does the Weierstrass function do? Well, it relates to the idea of elliptic curves, but we won't see these come back until later in the video. But what's an elliptic curve? Well, there's a few equivalent ways to describe it. One of them is a non-singular cubic projective plane curve. Okay, so what does this mean? You take some equation f of xy, which is a cubic, so something like x cubed minus 5 x squared y plus y squared, and you set that equal to 0. And hopefully this one doesn't have any singularities. Non-singular means it doesn't have singularities. Projective means that if you know about projective geometry, then you need to projectivize it. And plane curve just means that it's in two variables. Or I guess it doesn't really have to be a plane curve, it just has to be a curve. But there are some other equivalent ways to describe it. And the second way is what's called the Weierstrass model. And this essentially says that any curve of this form can be brought into the form y squared is equal to x cubed plus a 4x plus a 6. I believe those are the right coefficients. And I should mention that this, if you care about working things in positive characteristic, then this only works in characteristic 0. If you're working in characteristic 2 or 3, you need some extra terms. But I'm going to be doing this video talking about functions over C, so we don't have to worry about that. And what this says is that if you take any equation of this form, then you can apply some change of coordinates to get into this form. And I'm pretty sure in general it's like some weird rational change of coordinates, so you'll have to put in a little bit of work to see what the general thing is. But it turns out that anything can be put into this form, and we'll see this show up a bit later. But the third interesting way to describe it is a non-singular genus 1 curve. So what does this mean? Well, C is essentially like R2, right? So if we look at a curve in the plane, like the solution to this equation in the plane, then we're going to get something that looks like this. And this means that locally it looks like R. But if we look at the solution to this equation in C2, so if we say f of x, y is equal to 0, the set of all points would satisfy this in C2 instead of in R2, then what's going to happen is we're going to get something which locally, instead of looking like R, it'll look like C. So in other words, it'll be a two-dimensional thing. And it turns out that if you have a cubic curve, then C2 is like some R4, right? And the solutions to this equation in C2 turn out to trace out in a torus. So in order to visualize this, I mean, you just have to visualize four-dimensional space somehow, and then look at the space of all solutions to this equation in four-dimensional space, and it turns out that you get a surface, which is a torus, which is a bit hard to see. But in this video, I'll be sort of explaining a different perspective, which allows you to see that the solutions to an equation of this form will give you a torus in C2, and that runs through the Weierstrass function. And I guess it would also be nice to mention that this statement over here also implies that it's genus 1 automatically, even without this whole P function theory, by a very nice argument called the genus degree formula. Okay, so the other side of things that we want to work with is periodic functions. So we're going to turn 180 from elliptic curves and not talk about them for a while. And talk about periodic functions for a bit, and then see that ties back up to elliptic curves in the end. So I'm going to start by talking about something that you guys definitely know, which is just sine of x and cosine of x. Okay, so what do the graphs of these functions look like? Well, this is sine of x, this is cosine of x. And so what are some important properties of this? Well, you might disagree, but I would argue that the most important property of this is that sine and cosine are periodic. In other words, after 2 pi, they start repeating themselves. So you have sine of x plus 2 pi is just equal to sine of x, and the same thing of cosine. And one thing that this grants you, or something interesting that you can do with this uh, trig functions, is you also have the fact that sine of x squared plus cosine of x squared is always equal to 1. And so this means that if you look at the points sine t comma cosine t, then they trace out the unit circle x squared plus y squared equals 1. So these two analytic functions trace out this algebraic equation x squared plus y squared equals 1, which is, hopefully by the end of this video, you'll have a much deeper appreciation for this fact. But yeah, so one thing that you might have learned eventually is that these functions can be extended to the complex plane as follows. So for example, cosine of z is equal to e to the I z plus e to the minus I z over 2. Because, is that correct? Yeah, because this is just cosine z plus I sine z, and this is cosine z minus I sine z, and so that cancels and whatnot. And so you can look at z as taking values not only in the real numbers, but in the complex numbers. So this is the complex numbers, which is the input parameter z. And what we have is we still have that cosine of z is equal to cosine of z plus 2 pi. So that means that this value is the same as this value. Let's say that this line is 2 pi, this is 4 pi, this is not drawn to scale. But this value is the same as this value, same as this value, same as this value. And if we look at some other point, maybe not even a real point, but this value is the same as this value, same as this value, same as this value. So as you can see, the values are determined on this sort of vertical strip. So if you know the value here, then you know the value to the right, and so on and so forth. So to know all the values of cosine z, it suffices to know the values of cosine z in this little vertical strip over here of width 2 pi. So now we can ask what happens if you move in the imaginary direction. And well, what happens is, let's say that z is equal to I tau. So in other words, we're moving up in the imaginary axis. Well, then what happens is cosine z is equal to e to the minus tau plus e to the tau over 2. And this approaches infinity as tau approaches infinity. So we see is it's periodic in the horizontal direction with this sort of a graph, but as you move in the vertical direction, you're gonna essentially go to positive or negative infinity. Or sorry, the other direction also, if you do put in minus I tau, then you actually get the same expression. So you go to infinity on both sides. So we can naturally ask the question, do there exist so-called doubly periodic functions? And so what does this mean? So if we look at now our complex plane input, then we can say, okay, is there a function which is invariant if you translate to the right? And for convenience, I'll just say translate to the right by 1. So let's call this function p, and we'll ask, does there exist a function such that p of z plus 1 is equal to p of z? But then we're also going to ask that it's translation invariant vertically. So that means is p of z plus I also equal to p of z? So we want both of these to be true simultaneously. And so what you can deduce from this is that it must be periodic if you translate along any element of this lattice. So for example, this would be the input 2 plus I, and you can check that p of z plus 2 plus I is also the same as p of z. And so what that means is that if this is the square, 0, 1, I, 1 plus I, then if you want to know the input over here, well, you can just translate this back into the fundamental square, and then figure out the input over here. And it'll also be the same as the input as this point, as this point, as this point, and so on. And maybe if you chose like this point down over here, then that'll be the same as this point down over here, this point down over here, this point down over here, this point over here. So essentially, in every single one of these boxes, the function will be periodic because you can be periodic to the right and periodic upwards. So to know the entire values of this p function, it suffices to know the values inside this unit square. Now we can actually sort of generalize the framework a little bit. And instead of looking at things which are periodic with respect to this lattice, we can actually take two complex numbers omega 1, say, and omega 2, and we can look at so-called lattice generated by these two complex numbers. So this will be omega 1 plus omega 2, this will be negative omega 1, negative omega 2, uh, omega 1 minus omega 2, and so on and so forth. So you just like essentially take all formal linear combinations, z plus omega, z omega 1 plus z omega 2. So this will be the set of all n1 omega 1 plus n2 omega 2, where each ni is in z. And this defines some sort of a tiling of the complex plane, similar to how this one does it, and except instead of tiling in terms of squares, it's in terms of rectangles. And so we can ask the question, I'll call this set lambda, and we can ask the question, does there exist some function p of z such that if we translate by any element along lambda, the function will remain invariant. So in other words, p of z plus omega is equal to p of z for all omega in lambda. And so what this means is that if you want to know the function over here, then you can translate it by, say, omega 2 omega 1 minus omega 2, and then you know the function over here. Or you can also know the function over here or the function over here. And at all these points, the function will take the same value. So hopefully, I mean, this seems like a well enough motivated question that since we know functions sine and cosine, which are periodic, we can ask in the complex numbers, is there something stronger? Can we find a doubly periodic function? And so now we're going to embark on this journey to find such doubly periodic functions. So first I want to make some sort of observations of what such a function would have to satisfy. And for this, you would probably need to know a little bit of complex analysis. But if you want to black box these statements, then you can do that as well. So one thing that we want to say is that P of Z should be holomorphic. And what this means is just complex differentiable or complex analytic, or however you want to think about it, but functions which can be expanded as a power series in terms of Z. Okay, so observation number one, P of Z cannot be holomorphic. And so what do I mean by this? I.e., it must have poles. So what does holomorphic mean? I guess it even stronger than being expressible as power series, it needs to be expressible as a power series with positive coefficients in Z. So something like 1 over Z or 1 over Z squared is not holomorphic. And why is it true that P of Z cannot be holomorphic? Well, if it was holomorphic, then we would know the values of P of Z inside, or the values of P of Z inside this square would be the same as the values of P of Z inside this square, and every single square takes the same values. So because this square is compact, and P of Z is a differentiable function or a continuous function or whatever, then P of Z takes a maximum value inside the square. But then say this maximum value was like capital A. Then the maximum value inside this square would also be capital A. Same inside this square and same inside this square. And so what that means is that the absolute value of P of Z is less than or equal to A in, let's give this fundamental domain a name, let's call it D, implies that P of Z is less than or equal to A for all Z in C. And so by someone's theorem whose name I'm forgetting, but I really shouldn't be forgetting, this implies that P of Z must be constant. Because if you have a everywhere bounded holomorphic function, then that function has to be constant. This is a theorem from complex analysis. So now we notice that a constant function obviously satisfies these conditions that the function is doubly periodic because, well, every value takes the same value. So it doesn't matter if you translate it, it'll still take the same value. But that's a really boring function. So we shouldn't really count those as valid functions. We want to find something that's non-constant. And so what that means is that we have to include poles. And so instead of considering holomorphic functions, we should really be considering meromorphic functions, which means something that's almost holomorphic, but you introduce poles to sort of have a bit more freedom with things. And so what that means is that P of Z will look something like maybe 1 over Z cubed plus 3 over Z squared plus 9 over Z plus az squared plus 32, or I guess something, z cubed plus something, whatever. It'll be some series expansion like this. Now the thing is, we want it to be as nice as possible, so we want to have the minimal amount of poles as possible. This leads us to our second observation, which is that P of z cannot have only one pole. And why is this true? Well, we can use this lovely argument called the argument principle. And this says that the number of zeros minus the number of poles in some region R is equal to the integral over the boundary of that region of f prime of z over f of z dz. And so I guess I should say number of zeros minus number of poles of some function f of z is equal to this. And if you would like, then this is the derivative of log of f of z. And so the reason this is called the argument principle is because the log essentially sort of, or sorry, I guess it should be something like 1 over 2 pi I or something like that. So the imaginary part of the log sort of tracks the argument of a complex number. And so this says that the number of zeros minus the number of poles of a function is equal to sort of the winding number of your function around 0, which is sort of keeping track of the argument of f of z. And so again, this is another thing from complex analysis, which I'm going to use. But what I want to do is analyze this on the fundamental domain D. So the fundamental domain D, I guess maybe if this is the lattice 1i, then look like this. Or if you have some other lattice spanned by omega 1 and omega 2, then look like this. And so this is the region D. Okay. And what I want to do is I want to figure out, okay, how many, we know that P of Z has to have some poles in here, but I want to see how many poles it has inside. So the first thing that we can say is like, okay, let's try and minimize the number of poles, and let's say that we have only one single pole. So let's say that we don't have terms that look like this, and let's try to only have a term with one, like 1 over z inside this fundamental domain. And I'll show that that's not possible, and the reason is, let's compute the integral over the boundary of this region D of p prime of z over p of z dz. Okay, so now some observations about this integral is that 1 over p of z, because p of z is doubly periodic, 1 over p of z will also be doubly periodic, right? Because if these two have the same values, then their ratios will also have the same values. But sort of a deeper observation is that the derivative of the function will also be doubly periodic. And the reason is because we know that the derivative is a local thing, right? So we can compute it locally. And we know that, like, for example, these two values, these two inputs have the same value of p of z. But also, if we look at two small little neighborhoods, then these two small little neighborhoods will also have the same values of p of z. So what that means is that if we compute the derivative by looking at like p of z plus w minus p of z over w in these two regions, then they'll be the same because p takes the same values in those two neighborhoods. So what that means is that p prime will also be a doubly periodic function. Okay, so what that means is that this whole guy, if you take the product of doubly periodic functions, again, that's doubly periodic function because, you know, if these two things take the same values, if two functions take the same values at two different points, then the product of them will also take the same value. So this is also some doubly periodic function. Okay, so what does that tell us? Well, what it means to integrate over the boundary of this region is we integrate over this side, this side, this side, and this side. However, because it's doubly periodic, the values of this function will take the same value over here as it does over here. And it'll also take the same values over here as it does over here. So let's call these side lengths 1, 2, 3, and 4. So this will be the integral over 1 of something, plus the integral over 2 of something, plus the integral over 3, plus the integral over 4. And so what happens is that the integral over 3 is going to be exactly negative the integral over 1. Why? Because this argument here is doubly periodic, which means that if you translate by w2 and go from this edge 1 to 3, then you'll be taking the same values. But because you're going the opposite direction, you pick up a negative sign. And similarly, the integral over 2 will be the same as the integral over 4. And so what this tells you is that the integral over these two sides will be the same. And now I'm realizing that I actually proved something which I was supposed to prove a little bit later, but that's okay because the same sort of thing. And so what this tells you is that this whole integral is 0, which is the number of zeros minus the number of poles. Okay, so what I've actually proven for you now is that the number of zeros of this function inside the fundamental domain is always going to be equal to the number of poles in this function inside the fundamental domain. And by the way, we're actually going to choose the poles to lie at 0, but you can actually shift the fundamental domain a little bit over so it avoids 0. But what I actually want to do was, instead of doing this integral, I want to take the integral of p of z over this region. And so by the same reasoning, because p of z is a doubly periodic function, this integral will also value to 0. But we know that this is equal to 2 pi I times the sum of the residues over, I guess, like zi, which are the poles of p at zi. And so what is the residue? It's the coefficient of this 1 over z factor if you have a pole of order 1, or if you have a higher order pole, it's just 1 over z factor. And then because this is equal to 0, we see that we can't have a single pole of order 1 over here, because if at this point it'll look like 1a over z minus zi plus z minus zi squared or something like that. Then what will happen is that this contributes a value of a to the pole, and that's an issue. So what that means is that we need at least 2 poles, which can either mean two single poles like here and here, or 1 double pole. And what we'll choose to do is have 1 double pole at the origin and look at what the consequences are. And by this other statement that I made and accidentally proved a bit too early, the number of zeros inside a fundamental domain will also be 2, because the number of zeros minus the number of poles counted by multiplicity is the same. Okay, cool. So with that preliminary out of the way, let's try and do the following thing. So we have some lattice over here. I'm so sorry that I'm really bad at drawing lattices. But we want some function which has a double pole at 0 and is also doubly periodic. So what that means is that near 0, our mystery function p of z is going to look like 1 over z squared plus some other stuff. And notice that there won't be a 1 over z term, so really this will look at like some a0 plus a1z plus a2z squared, and so on and so forth. There won't be any negative terms more than that, or at least we're trying to find a function which doesn't have any negative terms. And we also want it to be doubly periodic. And so what does this force upon us? Well, because it has a double pole over here, that means it also has to have a double pole over here, and a double pole over here, and a double pole over here, and a double pole over here, where this is omega 1, omega 2, like omega 1 plus omega 2. And so what this tells you is that P has a double pole at omega for all omega in our lattice, which, remember, is linear combinations, integer combinations, I should say, of omega 1 and omega 2. So if we write this out, then what that means is that we can write P as being, or at least it should have the sum of all omega in our lattice of 1 over z minus omega squared. And so what does this look like? Maybe it'll have some other terms as well, but it at least needs to have these terms so that we can guarantee that it has a double pole at every point. So for example, at omega 1, it'll look like z minus omega 1 squared. In case you aren't convinced that it has a double pole at every point, because it doesn't really make sense to say double periodicity if their value is infinity, you can look at like the behavior at nearby points. And again, the behavior at nearby points needs to also be the same if it's doubly periodic. And because the behavior at nearby points says that it has a double pole over here, it also say that it has a double pole over here. So what this will look like is 1 over z squared plus 1 over z minus omega 1 squared plus 1 over z minus omega 2 squared plus other terms, and then plus possibly even more other terms. But I claim that we don't actually need any other terms. In fact, once we have the sum, then we're already done because we have found something that is doubly periodic that is non-trivial. And so how can I show that? Well, let's look at what P of Z plus W, let's say W tilde is, where W tilde is some element in our lattice. So if we plug this in explicitly, then what this will be is sum over omega in our lattice of 1 over Z plus W tilde minus W squared. But the thing is that this is actually the same exact sum as this. Why? Because I can rearrange it to be the sum over omega in lambda of 1 over Z minus W tilde squared. And the thing is, because W tilde is in our lattice, W minus W tilde, as W varies over our lattice, will also vary um, over our lattice. So um, what does that mean? Like if we take the sum and let's say that W is equal to W1, then suppose initially we counted like, okay, we're gonna add this term and then this term and then this term and then this term. Well, now instead what we're doing is we're first adding this term and then this term and then this term and then this term. So we're just shifting everything by W1, but we're still adding every single element of our lattice. And so we can just replace this as saying the sum over all W prime in our lattice of 1 over Z minus W prime squared, where W prime is equal to W, I guess, W minus W tilde. And this is just equal to our original P of Z. So we found something that's doubly periodic. Except that there's one small problem, and that is that it turns out we have to be a bit careful when we're adding things. So if we usually think about like sums over the integers, right? Or sums over the natural numbers, then we have like the sum of some sequence an from n equals 1 to infinity. And the thing is, there's a canonical order to add these in, which is a1 plus a2 plus a3 plus 1 and so forth. But it turns out that in some cases, like if you add them in other ways, then you might get different answers. So for example, if you have a sequence an where you have a subsequence an1, an2, and so on and so forth, which converges, or not converges, but which diverges to infinity, and you have some other sequence an1 prime, an2 prime, and so on and so forth, which diverges to negative infinity. So in other words, terms of your sequence which get more and more positive, and terms of your sequence which get more and more negative. Actually, I don't think this is right. Such that the sum of a and I is infinite, and the sum of a and I prime is negative infinite. Then what that means is that you can rearrange the terms to be any value actually wanted. So what do I mean by this? Let's look at an example. You have the sum 1 minus a half plus a third minus a fourth, and so on and so forth. So plus a fifth minus a sixth. And if I remember correctly, then this is equal to the natural log of 2. Okay. And what that means is that if you truncate the sum after long enough, say plus or minus 163, then that'll be like pretty close to the natural log of 2. What we can do is we can look at the sum of the positive terms, 1 plus a third plus a fifth, and so on and so forth, and look at the negative terms, negative 1/2 minus 1/4 minus 1/6, and so on and so forth. And what we'll notice is that this sum approaches infinity and this sum approaches negative infinity. And the reason for that is essentially because the harmonic series diverges, and so these two are pretty close to harmonic series. You can guess that this is exactly half of the harmonic series, and this one's, you can do some manipulations for that. So now what you can do is you can actually manipulate the sum to get any value that you wanted. For example, what I can do is say I want to get the value of 4. So what I can do is, let's look at the number line. I could first add 1, and then add like these positive terms until I get just bigger than 4. And then I add on these negative terms and go left until I get just below 4. And then I add positive terms again until I go to the right of 4, and negative terms again until I get to the left of 4. And then I keep playing this game where I keep going back and forth around 4. And the thing is, because these numbers keep getting smaller and smaller, they will converge. So if I add these up in a different order, I can get to 4. In fact, I can get to any real number that I want to in the same fashion. So what that means is that order really matters over here if your convergence is not good enough. And we see that over here, like the convergence is like the harmonic series, which is like very delicately convergent if you have something like derived from it, which is convergent. And so it turns out that this guy is also very delicately convergent. And what I mean by delicately convergent is like if you have something which is absolutely convergent. And so what that means is that not only does the sum of an converge, but the sum of the absolute value of an also converges. Then this issue won't matter. No matter how you add up the sequences in order, no matter what order you add up the sequence in, even if there's positive and negative terms, it'll converge to the same value. And so you can see here that this is not true because if you add 1 plus a half plus a third plus a fourth and so on and so forth, then this sequence is the absolute convergence of the sequence is the harmonic series, which diverges. However, if you look at, for example, 1 minus a quarter plus a ninth minus a 16th and so on and so forth, whatever this sum is, it doesn't matter what we add our terms up to, because if we take the absolute values of these terms and take the sum, then that converges, and so it doesn't really matter what order it is. So it turns out that this sequence, the same thing holds for complex numbers, by the way, if you take the sum of complex numbers, but this sequence is actually not absolutely convergent. And so what that means is it actually matters the order in which we sum up our lattice points. And the problem with that is when we translate by some omega tilde, then that changes the order in which we sum up the lattice points, right? So how can we show that this is not absolutely convergent? Well, I'll give you some heuristic argument. So let's analyze the sum p of 0. So obviously p of 0 doesn't really make sense because p of 0 is just infinite, as I showed here. But what I really mean by this is let's look at this sum, which is omega inside lambda minus 0 of 1 over omega squared. So what that means is like get rid of the term 1 over z squared, but keep the rest of them, and then plug in 0 for the rest of them, and look at what this sum is equal to. And actually what I want to analyze is not this, but the sort of absolute values of the summands. So it'll be 1 over absolute value of omega squared as omega varies in our lattice minus 0. Okay, so what I want to show is that this sum diverges, and thus this sum is not uniformly, absolutely convergent. So how can I show this? Well, I'll give a little heuristic argument for it. So let's say this is our value 0, right? Let's say this is omega 1, omega 2. So we can split this up into sort of layers, where this is the first layer, which is either like omega 1 minus omega 1 minus omega 2, or omega 1 plus omega 2. And then we can go to the next layer, which is like this. Do I have enough points? Something like that. And so this will be like 2 omega 1. Say this will be like omega 2 omega 1. No, sorry. This will be omega 1 plus 2 omega 2, and so on and so forth. So essentially the first layer is the ones where the coefficients of omega 1 and omega 2 are at most 1. Here the coefficients of omega 1 and omega 2 are at most 2, and so on and so forth. So what we can do is we can, because all these terms are positive, if it were absolutely convergent, we could add it up in any order we wanted. So what I want to do is sort of add it up in these layers and see what the sum of 1 over absolute value of omega squared is in these layers. And so heuristically, all of these layers are almost like circles, right? So this is almost a circle of radius r. This is the absolute value of omega, I should say, is approximately r. The absolute value of all the omega in this second layer is approximately 2r, and in the third layer would be 3r, and fourth layer would be 4, and so on and so forth. So what we can do is then we can take the sum of, how should I write this? 1 over n r squared, and then we want to take the sum over n, and then we want to take the sum over the number of omega in the nth layer. So this is saying for all the omega in the nth layer, the absolute value of omega is approximately equal to 1 over nr. And so if we take the sum of all those omegas in the nth layer, and then we take the sum over all of n, then we'll approximately get the sum over here. It should say this is approximately equal to. Okay, so how can we evaluate this? Well, in the first layer, how many points do we have? 1, 2, 3, 4, 5, 6, 7, 8. So in the first layer, we have 8 over r squared, right? In the second layer, um, ignore that. In the second layer, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 points. Okay, so that'll be plus 16 over 4r squared. And I'll leave it as an exercise to show that in general, what you'll have is 8n points in the nth layer over nr squared, which this guy is equal to 8 over nr. Okay, so what we see is that the sum is the sum of 1 over absolute value of omega squared is approximately the sum from n equals 1 to infinity of 8 over n r, where r is just some number, which is, let's say that r is equal to the absolute value of omega 1. Or like you can take the average of omega 1 and omega 2. I'm not really being too precise with the inequalities here, just to give you an idea of what's going on. But we see here that this is the harmonic series, and so this diverges. And so unfortunately, we do not have an absolutely convergent series. However, as I said, the harmonic series is not super bad because it's like just barely convergent, and so it's like almost convergent. If we handle it in a very delicate manner, then it turns out that we can fix convergence properties all the time. So to rewrite what I had, we had that P of z is equal to the sum over omega in lambda of 1 over z minus omega squared. And what we've just noticed is that the sum of 1 over absolute value of omega squared for omega in lambda, but omega non-zero, this is approximately equal to the sum of 1 over n. So what we can do to actually fix this divergence is actually just subtract off the bad terms. So what we can do is we can subtract off 1 over omega squared from each summand over here, and then only include the summands over here which are non-zero, and then add on 1 over z squared. And so if we take this expression, it turns out that this sum is actually uniformly convergent. And so it doesn't matter what order we take the sum of our lattice points in. And so it turns out that this is, in fact, a valid doubly periodic function, which is meromorphic and converges and everything else. And so maybe there's a couple things that you might not like about this. One is that it doesn't exhibit the same level of symmetry that we had over here. We just had sum over all omega in lambda. Over here, we're like kind of singling out the omega equals 0 case. But there's sort of two ways to convince yourself that this doesn't affect the fact that this is doubly periodic. The first is, in a sense, all we're doing is we're subtracting a constant. And as we said earlier, a constant is doubly periodic. And the sum of two doubly periodic functions is also doubly periodic. So this should still be doubly periodic. Now, I mean, I guess you can argue that we're adding like an infinite constant, but like whatever, that's just a heuristic. Another way that you can sort of get at this formula is you can note that p prime of z should also be doubly periodic. And so if we ignore this term, then p prime of z would be sum of 1 over z minus omega cubed, maybe some constant term over there. But then if you computed the absolute value of 1 over absolute value of omega cubed, then this will approximately be the sum of 1 over n squared. And so this does absolutely converge, and so you're good there. And even though this sum did not converge, this one does. And so what you can do is then define p of z to be the integral of p prime of z. I guess p prime of z bar dz bar going from 0 to z. And if you do that, then you'll end up getting something like this, which comes from subtracting off the value of this guy at 0. And you want to like ignore the pole at 0 there, whatever. Okay, cool. So now we have this doubly periodic function, EA. What can we do with this? Well, I'm gonna throw some black magic at you and show that this actually relates to elliptic curves. So the first thing that I want to do is I want to expand this as a power series. So in other words, 1 over z squared plus some other stuff. Okay, so what will the other stuff be? Um, well, let's expand these summands as um, power series at the origin. And what that'll give us is 1 over z minus omega squared is equal to 1 over omega squared um, times 1 over 1 minus z over omega squared. Um, and so let me cheat a little bit and recall what this power series is equal to. Um, okay, so this will then be 1 over omega squared times 1 plus the sum from n equals 1 to infinity of n plus 1 z over omega to the power of n. And so one way that you can get at this is you know what the power series of 1 minus z over omega will be. It'll just be the sum of um, z over omega to the n. And you can sort of integrate that to get this one over here. Okay, so now what that means is that if we subtract 1 over omega squared from all of these, then what that'll do is it'll get rid of this one term. And we see that each of these summands contributes this guy at 0. So if we collect terms of z to the n together, then what that'll mean is that we have 1 over z squared plus the sum over omega in the lattice. I'll call it lambda star to be lambda minus 0. And now we have n plus 1 times z over omega to the n, sum over n equals 1 to infinity. And then what you get is that this should be, 1 over omega squared. So this will be 1 over z squared, and then you can argue that you can flip the summation of the lattice and this guy by absolute convergence or something. And then what you get is z to the n times the sum over omega in lambda star of 1 over omega to the n plus 2. Okay, cool. So now I want to argue for you that this sum, I'll call it Gn. I want to argue that Gn equals 0 for n odd. And there's two ways that you can see this. First off, I should mention that by calling this Gn, I essentially have exhibited a power series here, n equals 1 to infinity of Gn z to the n. So for n odd, we note that p of z is equal to p of minus z, just by looking at this expression over here, or if you like, ignoring this constant term and just looking at the expression, the more symmetric expression, you can see that p of z equals p of minus z. And so what this means is that we shouldn't have any odd terms in our power series expansion. However, you can more directly see this by just evaluating the sum over here and noticing that if you swap omega for minus omega, then that'll put a negative sign on here because you have an odd exponent, but at the same time, you'll be summing over the same things. So the sum should be some value, but it should also be negative of itself, so it'll have to be 0. Okay, so what that means is that this will look like 1 over z squared plus g2 c squared plus g4, g4 z to the 6th, and so on and so forth. Z to the 4th, and so on and so forth. Okay, so now what I want to do is some interesting trickery. And that'll mean that I want to analyze this power series now, p prime z. So this will be negative 2 over z cubed plus 2g2z plus 4g4z to the fourth, and so on and so forth. And what we can do is we can square p prime of z squared. And so what we realize is that this will be 4 over z to the sixth plus some other terms. And I guess I don't want to go over the details because it's some annoying linear computations. But what you can do for this case is you can notice that if you take p prime of z squared minus 4 p of z cubed, then what happens is p of z cubed has a leading term 1 over z to the sixth. So it will be minus 4 times 1 over z to the sixth. And so this thing will have a pole of order, I think, at most z to the fourth, and then something of order z cubed, and then so on and so forth. And what you can do is you can keep playing this game of, so what happens is that you no longer have any z cubed because this is now an even function. And so this will just have a term of 1 over z to the sixth, I think 1 over z to the fourth, and 1 over z squared as well. So this will have some coefficient over z to the fourth plus some coefficient over z squared and some other terms. And so what you can do is you can add on multiples of p of z and p of z squared instead of p of z cubed. And what you'll find is that if you take the linear combination p prime of z squared, which will be this plus something over z to the fourth plus something over z squared, and you add negative 4 p of z cubed minus 60 g4 p of z, where g4 is this guy, minus 140 g6. Then what this will be is it'll be some power series which starts off at z squared, something z squared plus something z to the fourth plus something z to the sixth, and so on and so forth. However, so the main idea is that you take the square of this and then you cancel out poles by adding on multiples of p of z. However, the thing is, everything on the left is doubly periodic, right? P of z is doubly periodic, so p prime is 2, so is its square, so are these powers, so are linear combinations of them. So everything on the left side is doubly periodic. So that means that the right-hand side must also be doubly periodic. However, what we've done here is we've canceled out all the poles on the right-hand side. And so that means is that the right-hand side is a doubly periodic function with no poles. In other words, a holomorphic doubly periodic function. In other words, it has to be identically 0. So what we've interestingly found is that p prime of z squared is equal to 4 p of z cubed plus 60 g4 p of z plus 140 g6. And so I'll rewrite this as 4 p of z cubed plus g2 p of z plus g3. And if I suggestively make the substitutions, x equals p of z, y is equal to p prime of z, then what we'll notice is that if we sort of like make this parameterization, p comma p prime, similar to how we had like sine comma cosine, then what we'll find is that this pair of numbers will satisfy the equation y squared is equal to 4x cubed plus g2x plus g3, which, if you remember from the very beginning, was the Weierstrass model for an elliptic curve. And so what that tells you is that we've actually found a parameterization for the Weierstrass model of an elliptic curve. And what I want to do now is actually show that this actually hits every single point on the elliptic curve. Okay, so how can we do that? Well, you can analyze. What I'm saying is like these pair of numbers will be some point on the elliptic curve. What I want to say is that if you have an arbitrary point of the elliptic curve, then there will be some z so that this pair of numbers will land you that point. So what we can do is we can analyze the points on the elliptic curve and then show that there's a value of z that satisfies that equation for every value of x and y that satisfies this guy. Okay, so let's say that we take some value x0. So some pair x0 comma y0 on the elliptic curve, which will be the set of solutions to this. So that'll mean is that y0 cubed is, y0 squared is equal to 4x0 cubed plus g2 x0 plus g3. Okay, so what I want to do is I don't want to like fix this y coordinate. I want to just let it be a random value y and see how many values of y satisfy this equation. So let's call this value c, or c0, I guess. Then we see that we have y squared is equal to c0. So there's two possible cases. Either c0 is equal to 0, in which case you have one value of y, which is y is equal to 0, or c0 is equal or is not equal to 0, in which case you have two values of y, which is y is equal to plus or minus c0. So when does this case happen? Well, this case happens when x0 is a root of this cubic polynomial, right? So I guess I can call this cubic polynomial like f of x. Okay. So in other words, they're exactly 3 x values. So we see that there are 3 x values for which there's exactly one value at which y is 0. And other than that, there are always 2 values at which y is 0. And this is the point at which I should have actually proven that there are an equal number of zeros and poles inside a fundamental domain. But oh well, I did that a lot earlier than I was supposed to. So what does that tell us? Well, let's analyze the points at which, let's see here. What do I want to say? Yeah, let's analyze the values at which x is equal to 0. Okay, so this will be like 0, comma, plus or minus square root of g3, assuming g3 is non-zero. So if we want to parameterize this point, then what we want to say is that p of z is equal to 0 and p prime of z is equal to this. Well, it turns out that there are exactly 2 values of p of z at which p of z is equal to 0. And why is that? Well, because p of z has 2 poles, and we saw earlier that the number of poles and the number of zeros counted by multiplicity is the same. So it turns out there are 2 values for z at which p of z is equal to 0. And you can check then that, okay, so I should actually also mention that because p of z is an even function, let's say that this is one of the values. So that actually can't be one of the values. Let's say that this is our fundamental domain, and this is one of the values at which p of z is equal to 0. Then that would mean that this is the other value which p of z is equal to 0, which will be equivalent to this point up here, because this is negative of this guy, so it has to take the same value because p of z is even, and then you translate it to be up there. Okay, well, let's analyze what p prime at these points are. Well, we know that p prime is an odd function, so whatever p prime, whatever value p prime takes over here, it'll take the negative of that value over here, and so it'll take the negative of that value over here. So that means is that at the 2 points at which p of z is equal to 0, p prime of z needs to take negative values from one another. And we actually know that that value is g3, and that's because p and p prime, we already know a priori that it satisfies this equation. So we see that we cover both of these points in our parameterization. The other, and it turns out that if we just like take x is equal to some arbitrary value c, and then y is equal to plus or minus square root of something, then we'll actually cover it by the same argument. And why is that? Because we can instead look at p of z minus c. And we see that this is equal to 0 at 2 points. And why is this true? Because p of z minus c, it doesn't change the order of the pole at 0. And so that means is that in a fundamental domain, you can still you still have exactly 2 solutions to your equation. And so that means that there's exactly 2 points at which p of z is equal to c. And by the same argument, you can show that the derivative will take on negative values. Okay, cool. So every point is accounted for. Except let's analyze these points at which we have a double zero. So at the points that we have a double zero, we know that y is equal to 0. And so we know that p prime of z should be equal to 0. So let's try and find how many points there are at which this is true. So we know that a priori there are like 3 points at which this is true because p prime of z has 3 zeros, but it turns out we can actually explicitly find out what these values are. And the values are, I claim, w1 over 2, omega 2 over 2, and omega 1 plus omega 2 over 2. And the reason is, because p prime is odd, let's say this is your fundamental domain, if we evaluate p prime over here, that'd be the same as evaluating p prime over here, because all we've done is translate to the left by omega 1. But at the same time, this is equal to negative omega 1 over 2. So that means that p prime of omega 1 over 2 is equal to negative p prime of negative omega 1 over 2, because this is just the fact that this is an odd function by the fact that it's a derivative of an even function. But this is also equal to p prime of negative omega 1 over 2, because this is translating by negative omega 1, and this is doubly periodic. So those two facts together mean that this value is equal to 0. And so we see that p prime value at this point is equal to 0. And similarly, you can show that p prime value at these 2 points are also equal to 0. So that means is that inside a fundamental domain, at exactly these 3 points, p prime is equal to 0, which correspond to the 3 zeros of f of x, which is pretty cool. So that means is that x comma y is equal to p of z comma p prime of z parametrizes the equation y squared is equal to 4x cubed minus g2x minus g3. I guess I say plus, where again, g2 and g3 are determined by these big G's, and these big G's are determined as these coefficients over here. And I want to say that this is similar to how sine and cosine parameterize the equation x squared plus y squared equals 1. And so I encourage you to like analyze the power series for like sine and cosine, see if you can do like some similar trickery over here to conclude just from like the analytic series that sine and cosine must satisfy this equation x squared plus y squared equals 1. And moreover, these are actually like more intimately connected than you think, because if you replace cosine with negative cosine, that still parameterizes x squared plus y squared equals 1. Or actually, no, cosine is correct. And the thing is that cosine is the derivative of sine. Similar to how here we parameterize with p of z and p prime of z, here we're parameterizing with sine of x and the derivative of sine of x, or sine of t, or whatever. And these relationships actually go a bit deeper. Okay, so what have I now said? Now I have this weird function, p of z, which is doubly periodic, and we've shown that p of z and p prime of z together satisfy this cubic equation. So what I claim is that we can use this to show that this cubic equation is now traces out a torus. Well, we can do that by the following argument, which is that notice that p and p prime are doubly periodic, which means that we know the values based on their values inside a single fundamental domain. So we can restrict our attention on a single fundamental domain and see that this is in one-to-one correspondence with the set of x comma y such that this equation is equal to 0, where this squiggly line is this equation right over here. However, there's some redundancy in the square, and that's because this left side can be translated to this right side, and this bottom side can be translated to this top side. So what we see is that really we should be thinking about the square not as a square, but as a square with the opposite sides identified. And by classical argument, it's a torus. And that's because if you pull out the sides, then you get a cylinder, and then the top and bottom sides would come to a circle, and if you pull them out together, you get a torus. And so what that shows is that we've explicitly parameterized this equation in order to get ourselves a torus. Okay, let's see if we can like say a similar thing about sine and cosine, right? So these are functions from R to R, and it's periodic with period 0 to 2 pi, right? So if we want to understand the output, it would suffice to look at the interval 0 to 2 pi. Okay, but it turns out that since you can translate from 0 to 2 pi by adding 2 pi, these should really be 2 points that are identified. And if we identify the two sides of an interval, topologically what we get is a circle. And so that tells us that because sine squared plus cosine squared is equal to 1, this tells us that without actually having to graph anything, suppose a priori we didn't know that the equation x squared plus y squared equals 1 traces out a circle. We can show because sine and cosine parameterize this guy, that it has to be topologically a circle. And what really makes this argument work is if we just took sine by itself, we couldn't uniquely distinguish points. Why? Because sine considers the point pi to be the same as the point 2 pi because they have the same output on sine. But if we consider the graphs of sine and cosine together, then there are no points on the interval 0 to 2 pi which have the same value on sine and the same value on cosine. So these two functions really just are able to separate any points on the interval. And similarly over here, p and p prime are able to separate any 2 points on this fundamental domain unit square. And so this sort of sets up a one-to-one correspondence from the unit square to the solution to this equation, similar to how this sets up a one-to-one correspondence between the interval with all set points identified to the solutions to the equation of the circle. In fact, we can go a little bit deeper. We can actually look at what happens if we look at the parameterization sine z, cosine z. Okay, this will still satisfy the equation x squared plus y squared equals 1. And by the way, here now I'm considering c as a complex number. This will still satisfy the equation x squared plus y squared equals 1, but now the set of solutions to this inside C2. Okay, so let's see here. What happens is we have our plane C, and we split it up into a bunch of intervals like this. And so what we do is we can sort of, similar to how we took this interval and identified opposite sides, we can take this whole strip and identify opposite sides. And what we get is a cylinder. And it turns out you can, explicitly do it out. You can see something exponentials that sine and cosine uniquely determine values on the cylinder. And so what that means is that the cylinder parameterizes the complex solutions to x squared plus y squared equals 1. Except if you know a little bit of algebraic geometry, then you might know that maybe not under C2, but CP2, which is the projective complex space, the solutions to this equation actually look like a sphere. And the reason for that is that we, well, there's a couple of reasons. One is that you can do this classical parameterization where you parameterize a circle in terms of a copy of P1, and that is by fixing a point on it and looking at all lines that pass through that point, and this works over the complex numbers as well. And so we see that the solution to this equation should be equal to P1, which is a sphere. Another way to see it is that if we look at the solution to this over the complex numbers, over projective space, then we're actually missing out on 2 points, which are the points at infinity. And so the projective equation is x squared plus y squared equals z squared. And if we said z equals 0 to get the points at infinity, then what we get is x squared plus y squared equals 0. And there are 2 projective coordinates for which this works, which is one I0 and 1 negative I0. So these are 2 projectively distinct points which satisfy this. And it turns out that these 2 compactify the cylinder into making it into a sphere. Okay, so how can we see that we should really be adding these 2 points to the solutions based on our sine and cosine? Well, as I said earlier, we can analyze what happens to sine and cosine as we move up in the vertical direction. So let's see here. Sine of z, if I remember correctly, is e to the iz minus e to the minus iz over 2I, while cosine z is e to the iz plus e to the minus iz over 2. So let's see what happens if we take z is equal to I tau and let tau approach infinity. So in other words, we're moving up here on the imaginary axis. In other words, we're moving up here on the cylinder and seeing what happens. Well, if we look at the projective coordinates, sine z, cosine z, 1, right? Then what happens is this will look like minus e to the tau plus e to the minus tau over 2I. So I've sort of swapped these around for a reason. And this will look like e to the tau plus e to the minus tau over 2, and then the stored coordinate will be 1. And so what you can do is you can divide through all of these terms by e to the tau and see what happens, or e to the tau over 2, I should say. And so this becomes negative 1 over I plus e to the minus 2 tau over 2 over I. And this should be 1 plus e to the minus 2 tau. And then this should be like 2 over e to the tau, and so on and so forth, or something like that. And then if you let tau go to infinity, so these projected coordinates are the same. But now if you let tau go to infinity, which means that you go up higher and higher, then what you get is that this term cancels, this term cancels, and this term cancels. And what you get is minus 1 over I, 1, 0. Or in other words, if you divide through by I, then this will be 1, negative I. I encourage you to check that if you let tau approach negative infinity, then what you end up with is 1, I, 0. So what we see is that like by an explicit parameterization, we're able to like recover the points in infinity over here. And we can actually see that the same thing happens over here because our functions diverge at 0, right? So if we look at like the projected coordinates p of z, p prime of z, 0, sorry, 1, which is our projective parameterization, then we can look at what happens at z is approximately equal to 0. And so what happens over here is we have something like 1 over z squared, 1 over z cubed, 1, which is projectively the same as z 1 z cubed. So by multiplying everything by z cubed, and then as z approaches 0, what we get is 0, 1, 0. And if you were to projectivize this equation, then what you would find is you would have y squared z equal to 4x cubed plus something else. And you would find that the only projective point on this curve is going to be 0, 1, 0, which is pretty cool because what we have found is that like you can use these parameterizations to find the points in infinity of these algebraic equations. And you can even sort of see that like, oh, okay, so like if we take the cylinder and we had said at the point of infinity up here and down here, and we sort of compress the two ends of the cylinder to sort of meet up with that, then we actually get a sphere. So there's a couple more things to say about this. For example, if you look at these coefficients Gn, then what you can do is you can treat omega 1 and omega 2, which are your basis for your lattice, as sort of variables parameterizing your elliptic curve. And then you can treat these guys as functions of those parameters, and these functions try to satisfy very nice properties, and they're called modular forms. If you want to learn more about that, you can look at this book, Modular Function Directly Series and Number Theory. This is where I first learned about this stuff. It's a very good book. And there's some other things that you can say. For example, like I show you that if you have such a function, p function, then it satisfies this elliptic curve. But if I gave you an arbitrary elliptic curve to begin with, can you recover for me like what values of omega will parameterize it? And it turns out that you can. And the way to do that is this guy is a group. And it's a group because topologically it's S1 cross S1. And usually the point at infinity over here that we just worked out is taken to be the identity of the group. And so what you can do with a group is you can find an invariant one form. Okay, so wait, I should first say why these are useful. So we're trying to compute the values of omega 1 and omega 2, which will give the lattice. And what we notice is that this value is omega 1. What we can do is we can integrate dz from 0 to omega 1, and we'll get omega 1. But if we integrate dz from 0 to omega 2, then we'll also get omega 2. So we can figure out the two values of the lattice points just by doing this integral. And in fact, something else about dz which is remarkable is that d of z plus omega is equal to dz. So one other thing that you can do with this is like you can use this explicit parameterization to recover the algebraic group law of an elliptic curve. Another thing that you can do is like so what this means is that it's translation invariant with respect to the group law, whatever that means. And so if you can find a translation invariant one form of your equation which looks like this, then you can sort of integrate that along some loops to get the periods, which are these values omega 1 and omega 2. And it turns out that the invariant differential will look like dx over y. And so what you want to do is you want to compute the integral, some integral of dx over y, which is the integral of dx over the square root of 4x cubed plus g2x plus g3. And so this actually goes way back before this work of the Weierstrass equation, and these are called elliptic integrals. And so like these will spit out the values of omega 1 and omega 2 if you take the integrals over the right contours in the complex plane. But solving these elliptic integrals were actually what like motivated the study of all these things, and that's why these guys are actually called elliptic equations now. Yeah. So the last thing that I sort of wanted to say about this, I mean, there's a lot more that can be said here, but something that's interesting is that we can parameterize a sphere and we can parameterize a torus by analytic functions. And so we can ask, just maybe like an interesting topological question, is can we also find analytic functions which will parameterize higher genus surfaces? So if I give you a genus 2 surface, or like can I find some functions which parameterize some genus 2 surface living inside C2? And so hopefully I'll make another video discussing this topic. And there's some really interesting generalizations of these ideas, which lead you down to some interesting results.